So in chapter 11, we're going to be talking about analysis of data sets. Simple data sets are just sets of numbers like this. They can be collected from scientific experiments, just from observation. For example, these numbers here might be the result of if you asked a bunch of people how many siblings they have. We're going to be talking about measures of center and variation. Before we can find any measures of center or variation, the first thing we need to do with any data set is rearrange them in order, either ascending or descending, but I prefer to do ascending, so we'll rewrite them all from least to greatest. When we talk about the mode, we're talking about the number that appears the most times in the data set. So in this data set, our mode would be 3, because 3 appears the most out of any of the other values in the data set. 6 only appears twice, 5 only appears twice, 3 is our mode. When we talk about the mean of a data set, we're talking about the average value. So when we find the mean of a data set, we sum up all of the values together. So in this case, all of these numbers added together becomes 38, and we divide it by the total amount of values. This data set has 10 recorded values, so we put that number on the bottom, and we divide the top by the bottom to get 3.8. This shows us that our average value is 3.8. When we talk about the median of a data set, we're talking about the value that lies at the midpoint of that data set. What you could do with the data set is start at the outside of the data set and go 1, 2, 3, 4. Oh, it looks like the median is going to lie in between these two numbers. So we would average those numbers and we would find that the median, or the value that lies in between 3 and 4, is 3.5. However, if we had a very large data set, let's say we had 85 numbers, we wouldn't want to do the thing where we start on the outside and we count all the way in. That would take forever. There's a formula that will help us find the place of the media in the data set. So the formula for finding the place of the median in the data set is given as n plus 1 divided by 2, where n represents the total amount of values in the data set. If we're going to fill this in with our data set here, our value for n will be 10 because we have 10 values in this data set. So what we would do is plug in 10 plus 1 divided by 2. We would then get 5.5. Now note that this is not saying that the median is 5.5. This is saying the place of the median is 5.5. So what that means is if you look at your data set and count 5.5 values, that will be where your median lies. So let's do that. So looking here, let's assume that we don't know that the median is 3.5 already, and we'll count 1, 2, 3, 4, 5.5 values, saying that the median lies between the 5th and the 6th value of the data set. So this tells you the place, but not the value of the actual median. Using that same data set, let's talk about outliers. An outlier is a value that is much greater or smaller than the rest. For example, with this data set, which we previously used, an outlier might be if I additionally had the number 256. Obviously, all these numbers are much smaller. When we were finding our measures of center, so if we were finding our mode, our median, our range, the data set would be hugely impacted by this outlier. So outliers generally tend to tell you that something is off with the data, something happened there, we're not sure what, but it's not normal. The last concept we need to know about is standard deviation. Standard deviation is a way of measuring how far data values, on average, vary from the mean. Let's look at these two data sets I have here. These represent percentages on test scores from two different classes. We can see that on this test, all the data values are pretty close together. I mean, our range is really small. We only have from 78 to 85. So we can assume the mean of this data set isn't going to be too different from all these different values. The mean of these data points is 80.83. And we can see that 78, 79, all these values are not too far away from 80.83. So our standard deviation is going to be really small. With this data set, we can see that these values are spread out hugely, and none of them are very close to each other. Someone got a 25, that's not great. Okay, so the mean of this data set, if we average all the numbers together, our mean is going to be 68.25. Well, here's the problem we see with this. The only data value in this set that's remotely close to our mean is 62. But the difference between 68.25 and 25 is huge. The difference between 68.25 and 99 is huge. That means our standard deviation is going to be quite large. This ties into something we're going to talk about a little bit later, but I'd like you to see the picture so that you have it in your head for when you're doing this assignment. Here we see something known as a bell curve, which is also a representation of normal distribution. This is a representation of mean and standard deviation. So let's say that I take the test scores of many students from all over the United States. So this point here represents the average of whatever the data is. We could say that the average or the mean of the test scores is around 80%. So in this case, your y-axis would represent the total amount of students who got that score. You could see from here, the majority of the students got the average score. However, we have the 68, 95, 99.7 rule. So if we take 68% of all the data, so no matter how many data points we collected, 68% of those data values would be within one standard deviation. So going to the right of the mean or to the left of the mean, you could say, okay, 68% of that data will fall inside that category. Likewise, with a normal distribution, so what we would expect, 95% of the data values would fall within 2 standard deviations of the mean. So the 99.7% rule states that, okay, like you might have guessed, 99.7% of the data values are expected to be within 3 standard deviations of the mean. Okay, let's see this in action. How do you actually calculate standard deviation? So here's the data set we're going to use to the right, and for your convenience, I've already listed them from least to greatest. The first step we do is find the mean of the data set. When we calculate the mean, we add all these values together and divide by the total number of values. So our sum is 40, and our n value, so the sample size, is 8 because we have 8 total values. If we divide 40 by 8, we get the mean is equal to 5. So the next step is to subtract each data value from the mean and square the result. So starting with the first data value, I'll take 1, subtract 5, then I square it, getting positive 16. I'm going to repeat this with every single data point in the set. So once I've gone through with every single data point, subtracted it, and squared the result, I now have an entirely new data set. Now I'm going to find the variance by averaging the data from step 2. So we're taking all the differences from the mean, and we're going to average that. So once I add up all these numbers, 16 plus 1 plus 4 plus 4 plus 9, I'll get 38. And again, my total amount of data points is 8, so I divide by 8 again. So my variance is now 4.75. The last step is to square root the variance, meaning that you square root whatever you got in step 3. So once we averaged all the differences from the means, we square root that number, and we get 2.179. Let's interpret what this means. The standard deviation is 2.179. That's saying that in this data set, the mean is 5. And the average difference in that data set from the mean is around 2.179. This is a pretty low standard deviation. So going back to our bell curve, we know that the mean in this data set is 5. So if we're going to recreate our chart from earlier, we know that 68% of our data points, if this is a normal distribution, will probably fall within 1 standard deviation. So to find the upper and lower limits of our 68%, I took 5, and for the lower limit, I subtracted 1 standard deviation, and then for the upper limit, I added 1 standard deviation. So 68% of our data should fall within this range. Continuing with that same idea, if I'm going to now find our 95%, which is within 2 standard deviations, I could take this number and then find upper and lower limits again by adding 1 standard deviation this way and subtracting 1 standard deviation this way. So if I add another 2.179, I should find that, okay, 99% of our data falls within these ranges. So if we look at our original data set, we see that indeed that's true. I mean, all of the data fits within the 2 standard deviations of the mean, and most of the data falls within 1 standard deviation of the mean.